Okay, so we're now going to look at what we call influence diagnostics. And the whole idea of this is maybe some of your points don't lie near the rest. Is that causing a problem? So sometimes we'll get what we call potential outliers. And the idea is that when we see these, we want to know, are they having a major impact? Now, the first thing to basically say is, however much you have a point that sticks out, you do not remove it. I'll repeat that. You do not remove it. You might look at it and go, that sticks out. And then you go back to the person who gave you the data and go, could that point be wrong? If it's entered wrong, then you correct it. And you make a note to yourself that you corrected it. But if it's right, you leave it in. Now, what I will often do is I will do my modelling both with and without these points to see if it makes a difference to the final model, and then put forward both models for people to discuss. But what we're going to talk about now is how we actually diagnose the fact that these might be a problem. So first of all, we've talked about the studentized residual. Remember, that's the residual that is the difference between the model and the fitted model when the fitted model has been based upon fitting the model without that point. And we also, talked about the fact we'd standardize it so it has the right variance. Now, if you have a large studentized residual, that may be a problem, but it may not be. It depends on its leverage. So the two things that we have to take into account when we consider a point is its residual and its leverage. So what do we mean by leverage? What I mean by leverage is this point lies a long way away from the other points in the prediction space. So in this particular example I've got here, we've only got a single predictor, x. And you can see that this point over here sticks out. It's a long way. All the red points, the rest of the points are over here. It's a long way away in terms of predictor space, or in terms of x. Also, you can see that it's actually quite a long way away from the line. And so what I've done here is I have two models. The red line is the model I fitted when I didn't include that point, and the blue line is when I include the point. And what you should notice is the intercept has changed a lot and the slope has changed a lot. This is what we call an influential point. Here's one now where it's got a huge residual. But it's not too bad when it comes to the leverage, low leverage. And so it sort of moves the model up a little bit, but the slope's still the same, the intercept's slightly different. So it's not having a huge influence on the model. Here's one now where we have a small residual. So it's only a part away from the line. And you can see it's got huge leverage. So huge leverage, small residual. Again, the red line and the blue line are pretty similar. It's not having a big problem. And then finally, here's a normal point to some extent. Small residual, low leverage, makes no difference. You can't see, if you look very careful, you can see the red line just under the blue line. So we've got this idea of leverage, and leverage is this concept of, in any particular point, how far is it away from all the other points? And we saw in that very first plot how that can have a big problem. You have huge leverage, you're a long way away. And it's like leverage as in a lever. If you're a long way away, you can lift things more. You can pull that model, especially if you had a high residual. So how's it defined? Well, the leverage of data point is called HII. And basically you calculate, you take your design matrix, and you do the x transpose x to the minus 1, x transpose, times that by x, and take the ith point. So you find your points along the diagonal that compares with that. So if you just want to look at the individual point, it's going to be the, for that individual point, xi transpose x to the minus 1, xi. But basically you create this leverage and you look along the diagonal and look at those points. For the case of linear regression, you can see that it ends up coming by, you can do the actual calculations, hi equals 1 over n plus xi minus x bar. So basically you see the leverage is all about how far you are away from the mean of all the other predictors. Sorry, all the other points for that predictor. Where SXX is the usual sum of squares. So when's leverage big? Well, what we could do is we could say, well, roughly, if we add up all our leverage, how much is it? Well, if we're going to add up all our leverage for each individual point, that's going to be a trace of our h. So we substitute in. Remember, I could take this x and put it at the back with a trace, and it's still the same. This is just an I p times p matrix. So it's just got P1s along the diagonal, the rest is all 0, so we add up all those P1s and we get P. So if I have n points, the average leverage is going to be P on n, and we can use that as a rule of thumb. So one thing you can do is you can do what we call an index plot. If you actually go plot, I think it's which equals 6, it will show you this index plot. You've probably never seen it, and if I remember, I'll do it in the cheese data set. So what we do there is we plot the leverage against I to have a look at them. And what you can do is we work on the principle that any one that has a leverage of basically 2 times the average, which is 2p on n, we should think about. So what I've done here is we have our load of points. I've just done a bar chart of the values. You can see this one is a long way away from the rest. And if we calculate the leverage and look at it, you can see it's got a huge leverage compared with the rest. Even these ones that are towards the edge start to have a reasonable leverage, but this is the one that you want to go and check. So how can we actually measure the influence? Well, what you could do is you could say, well, let's work out my coefficient estimates with the point in and without it and see if that makes a difference. Because if you suddenly put a point in and all the coefficients change, then you're sort of going, well, that's affecting my model. So if we let b hat be the full model and b hat I be the one where you've taken the ith data point out, well, one thing you could do is you could look at the full model and the distance between that and the model when you take the data out. But we know that individual coefficients have different variance, so we want to take that into account. And that's what this does. It's called the Cook's distance. It's called di squared. For each point, you're going to calculate this, and it's going to be the full model coefficients minus the model coefficients when I remove that ith point. We've got our variance of our full model, and then we've got this. So this basically is a complicated matrix form, but it's basically working out a sum of squares between your two models, adjusting for your variance, which in the case of ours is x transpose x. Normally the variance is -1 at the bottom, etc. You can work it out. And there's a simple form of this. You can get your leverage, you can get your, in this case, standardized residual, and you can see there's a relationship between them that does the calculation for you. And you can see that obviously it's this interaction between your leverage and your residuals that gives you the Cook's distance. So what do we do? As a rough rule of thumb, if you have a Cook's distance of greater than 1, you'd be concerned about that, because that's roughly all your parameters are changing on average by 1 standard error. And this gives us our classic plot. So here's the original data set. We knew this point we're concerned about. It's got high residual, high leverage. And if you fit your linear model and then you look at your plots, it's this plot we've seen before. So let's have a look at it. You got your standardized residuals on here. You could use your studentized, but ours defaulted to standardized. Each of these circles is a point. This is your leverage for each point. And you can see you've got these contours. So everything in this contour is less than 0.5. Anything between this line and this line, or this line and this line, would have a Cook's distance of between 0.5 and 1. And anything outside this point number 11 has a Cook's distance greater than 1. So leverage on the x, residuals on the y. You can see each point. And what we do is we look at this and we can see this has got high leverage. It's to the right. It's got a high residual. And its Cook's distance is significant. So we would go and look at that data set and say, did you enter that data wrong? Should we change it? Maybe we'll fit the model with and without and do a comparison. Okay, so the next thing is we're going to bring all this together in a case study, and this time we're going to look at how tasty cheese is. See you next time.